This lecture is on chapter 3.9 to 3.10 on lattice energy and the Born-Haber cycle. So in the previous lecture, we went over the formation of ionic compounds into crystal lattices. And so we need to figure out, why do these salts actually form? And so to think about why ions go from, so atoms turn themselves into ions, and why do ions form together into this crystal lattice, you need to actually take a look at the energetics associated with each different process. And so, isolating, there are several different processes involved in order for these ionic compounds to form. So, first, you have to isolate the atoms into their monoatomic gaseous form. You have the ionization energy that requires lots of energy input. You have the electron affinity that releases energy. But all of this needs to be energetically favorable in order for a spontaneous reaction to occur. So just like a ball wouldn't spontaneously roll up a hill, the formation of salt needs to be energetically favored. So if we take a look at this energy diagram shown um, on this slide here, we can take a look at the energetics associated with each of these processes. So first off, we see our energy number one, which is, so anything that is going, so our baseline energetics of atoms so this is for the formation of sodium chloride, for the sodium and chloride atoms just being in their atomic state, the baseline energy level, so if the y-axis here is the energy going upward, and so the baseline energy here is the black line. And so we can see anything that is a red arrow going up is an energy input, and anything that is a blue line coming down is energy release. And in order for a spontaneous reaction to occur, what we need to do is have our final energy be an energy release from our ground state, which means it's going to be lower in energy than our black that we started from. So if we take a look at our process number one here, this is the conversion of sodium solid into sodium gas. And so we know from boiling water and from performing other actions that it takes energy input in order to break the intermolecular forces to cause a solid to turn into a gas. So that requires an energy input. Next is the energy required to split chlorine gas, which is a diatomic, two chlorine atoms that are bonded together. You have to split them to get your atomic chlorine. So again, breaking that covalent bond requires the input of energy. The next, number three, this is the ionization energy. So the energy required to rip an electron away from a sodium gas. So that requires a large amount of energy. So at this point, we've had three different sources of energy input. Next, we see the the electron affinity, which is a release of energy caused by forming the chloride anion by adding an electron to our chlorine gas. So what we have here is an overall net increase in energy that it seems like to form sodium chloride solid. So energetically, this seems like a lot of work. So why is the formation of sodium chloride such a spontaneous process? Why do we see table salt not rapidly decompose to its constituent elements if it exists at such a high energy input from its ground state atomic form? So the answer to that lies in our crystal lattice itself. So as we mentioned in our last lecture, sodium chloride forms its ions and then arranges itself in this very highly ordered crystal lattice. And so this lattice is held together by what's called lattice energy, which is given the symbol of U. And so this lattice energy is the amount of energy required to break an ionic solid into its individual gaseous ions. So if the lattice energy is the energy needed to break apart the solid, if you took the negative U, so the negative of the lattice energy, is the energy that is released upon the formation of that crystal lattice. And so this lattice energy is defined by Coulomb's law. And so Coulomb's law states that the lattice energy, so in this case, the negative of the lattice energy, is so this is a Greek symbol called alpha. So basically, that means proportional to. So what that's stating is that the Coulomb's law has some other constants that we don't really care about right here in this course. So what we're saying is the lattice energy is proportional to this equation here. So where we have Z1 and Z2, which are the overall charges on the respective cation and anion, over d squared, where d is the distance between the ionic nuclei in the lattice. So the physical distance between our sodium and chloride ions in the crystal lattice. So if we want to increase the lattice energy, what would we have to do? So I would pause the video for a second and just think through what sort of factors that we have to change in order to increase our lattice energy. So the factors that we have to change to increase the lattice energy could be either one, to increase the overall Z1 or Z2. So increase the total charge on either the cation or the anion or both. So going from sodium, which is an Na plus, to magnesium, which is Na2 plus, would increase this Z1 term. Or changing from fluorine or fluoride, which is an F minus, to oxide, which is an O2 minus, would increase our lattice energy. So the higher the charge, the larger your lattice energy. Another thing that you could change is the overall distance between the ionic nuclei. So the smaller we make this denominator, the larger our lattice energy becomes. So the smaller the ions that you move or that you include in your crystal lattice, the larger the lattice energy, the more strongly it will be held together. Okay? And so if we take a look at some of the lattice energies of the formation of some different salts, let's take a look at the trends that we see and see if they agree with our understanding of Coulomb's law and the general trends that we just went over in the last slide. So if we take a look here, so we have a bunch of singly charged anions and then our doubly charged oxygen. And then this first group here talks about our +1 group of cations, our 2+ group of cations, and then aluminum for a 3+. So what we see, so I invite you actually to pause the video here and go through and pull out some of these general trends and see if they actually agree with the lattice energy equation defined by Coulomb's law. Okay, so some of the trends that you can observe here is first we're going to be looking at the Z terms, and then we'll look at the D terms second. So first Z. What happens when we increase the overall charge of either the cation or the anion? So if we look at the formation of an ionic compound, a crystal lattice with lithium, okay, so when we're dealing with singly charged, we have values around 750 to 1,000. But if we incorporate with a doubly negative charge oxygen, we see the group or the lattice energy jump up dramatically. And this is the case with all of our different cations. And so this shows that when we increase this Z2, we see a great increase in our lattice energy. The same sort of thing is observed with our 2+ ions. When we incorporate our 2-, we see another big jump. Same sort of thing present for our 3+ cations, mixing with our O2-. And then if we compare the charge on our cation, so look at our Z1 term, comparing the relative amounts for our +1s, our 2+, and our 3+, we can see that each time it gets larger and larger. So this totally jives with our lattice energy equation, saying that if we increase our Z term, we're going to increase our overall lattice energy. So second off, we take a look at our distance, D. So as we go from F- to Cl-, Br-, and I-, what we're doing is moving down on the periodic table. And so we can see that the overall, as we move down in the periodic table, what does that do to the ionic radius? So the larger on the table, the lower we are on the periodic table, the more energy levels that we're including that are filled with electrons. And so those higher energy levels extend a further distance away from the nucleus, which increase the overall radius of the ion. So as we go from fluoride all the way over to iodide, we see an increase in the overall diameter of those ions. So therefore, the interatomic distance, defined by the distance between the two nuclei within our crystal lattice, is going to be increasing. So as we see this d squared term increase, we see a decrease in U. And that's what we observe here with the data. In all of our different conditions, we see as we go lower on the table, we see a decrease in our lattice energy. So the data here actually do support very clearly our Coulomb's law assumption. So that brings us back to our energetic diagram. And so this energetic diagram, we give the name the Born-Haber cycle. So previously, what we introduced to you is this is the formation again of sodium chloride. So we had our energy input for the turning sodium solid into a gas, splitting diatomic chloride, the ionization energy of turning sodium into sodium ion, and then the electron affinity of adding an electron to chlorine to form chloride. And so what we said is we had this net energetic unfavorable situation where we had an increase in energy. And so the reason why sodium chloride actually forms is because of this negative U. So negative of the lattice energy causes a release of energy upon the formation of a crystal lattice. And so this negative lattice energy releases so much energy that now we have a net reaction which is energetically favorable. So the energetic state of forming that crystal lattice is much lower in energy than our ground state where our two sodium and chlorine atoms started out. So this is why our table salt doesn't spontaneously decompose into its elemental states on our countertops. Okay, so the key important takeaway from this is that the lattice energy is what makes the formation of ionic salts energetically favorable. That's very important. So next, if we were to take a look at the formation of magnesium chloride, we can see a similar sort of situation here and the real importance of our lattice energy. So here we have magnesium solid turning into a gas again, splitting of diatomic chloride. And then we have two separate ionization energies to rip away the two separate electrons to form Mg2+. So we have a big energy input for those two ionization energies. Again, now we have our electron affinity, so a release of a moderate amount of energy upon the formation of Cl-. But we have this huge now energy disparity between the two. And it doesn't become, so the formation of this magnesium chloride does not become energetically favorable until we have the release of the large amount of energy due to the negative lattice energy. And we can see that lattice energy is very large for this species because we're dealing with magnesium 2+, which is more highly charged. So that's going to increase our Z2 term. And then also magnesium 2+ is a smaller ion. So we're also going to decrease our D distance in Coulomb's law. So we'll end today's lectures with a couple quick questions for you to work over on your own, and we'll give you the answers for them. So which of the following ionic solids would you expect to have the larger lattice energy? Okay, so potassium chloride, sodium chloride, calcium chloride, magnesium chloride, or magnesium fluoride. Okay, so I would pause your video and work through these. Okay, so I'd like you to rank these. We can actually sort of rank these in an order of what their lattice energy should look like. Okay, so for this relationship, we're going to be looking for our lattice energy. It's going to be proportional to our Z1, Z2 over D squared. Okay, so we're dealing with potassium chloride, so that's going to be K plus and Cl minus. Sodium chloride, which is Na plus, Cl minus. Calcium chloride, Ca2 plus and Cl minus. We're going to have magnesium chloride, Mg2 plus and Cl minus. And then magnesium fluoride, Mg2 plus and F minus. Okay, so first we can compare our overall charges. So we can see that all of these three groups here each carry this +2 charge on their cation. So we know that these three are going to be our highest because the charges have our biggest effect on our lattice energy, which mean that these two here, the potassium chloride and the sodium chloride, are going to be our lower two. So when we're determining which one is going to be our lowest energy, we then move to our D term. And so we take a look at the relative positions of potassium versus sodium. And if we look at our periodic table, we can see that potassium is lower on the periodic table than sodium. And when you get lower on your periodic table, you get larger ionic radius. So we know that potassium is going to be larger and sodium is going to be smaller. So in order to maximize our U, we know that this D term has to be as small as possible. As we decrease D, we increase U. Okay, so we know that the potassium chloride is going to be the larger of the two, which means that this potassium chloride is going to be the smallest rank. So we'll rank this guy as number 5. Sodium chloride then therefore will be number 4 in our ranking. All right, so now we're going to be taking a look at our relative sizes of our remaining ions in our three higher ones. So when we compare fluoride to chloride, we know fluoride is higher on the periodic table than chloride, so fluoride is going to be smaller, and we know that chloride will be larger. Okay, so if we're comparing magnesium fluoride to magnesium chloride, we know the smaller is going to have a higher energy, so we know that magnesium fluoride is going to be higher and magnesium chloride will be lower. So the comparison between those, we know where they're going to sit. Next is calcium chloride. And so if we take a look where calcium is in our periodic table versus where magnesium is on our periodic table, we'll see that the magnesium is higher on the table than calcium, which means that calcium is going to be larger. So since calcium and chloride are both larger, or calcium is larger than magnesium, that's going to mean that D term is larger, which means that this is going to have the smallest lattice energy out of all of them. Okay, you have a large calcium ion and you have a large chloride anion. So that's going to give this a ranking of 3. So now we've already teased apart these two guys. We know that now magnesium fluoride is going to be ranked number 1 as our higher. Magnesium chloride ranked number 2. Okay, so this should be something that you should be able to work through on a regular basis in order to order a set of salts in order of increasing lattice energy based on their charge and ionic radius. Next, which of the following alkali metal halides has the larger lattice energy? Which has the smaller lattice energy? Explain. All right, so without actually putting in a name for each of these elements, be able to identify which one will be a larger lattice energy. So take a moment to think about that. Okay, so again, we're going to be looking at our lattice energy, which is going to be equal to Z1, Z2 over D squared. So for this problem here, we know that we're dealing with alkali metal halides. So that means we're going to be dealing with a +1 with a -1. Okay, and we don't know which actual elements that we're talking about here. So, but we do know that the Z1 and Z2 term are always going to be the same if we're talking about an alkali metal halide. Halide, by the way, means a halogen. And so now we're just simply looking at our D. So if we want to, so which has the smaller lattice energy? So smaller lattice energy to get smaller U, what we have to do is increase our distance between our nuclei. So which one, A or B, has a larger distance between the nuclei? The correct answer there would be A. Okay, next we have one of the images represents sodium chloride, and one of the images represents magnesium oxide. Which is which, and which has the larger lattice energy? Okay, so take a moment to think about that. Okay, so first off, we're going to talk about magnesium oxide, MgO. And so that's formed from magnesium 2 plus and oxide O2 minus. Sodium chloride is going to be talking about Na plus and Cl minus. Okay, so now if we're taking a look at, if we're comparing these guys now, first by talking, so we'll answer the second part of the question first. Which one has the larger lattice energy? So if we say lattice energy, U is proportional to Z1, Z2 over D squared. And we know that the dominating term here has to do with the overall charges. That means that magnesium oxide by far will have a higher U than sodium chloride. So a higher lattice energy for magnesium oxide than we would have for sodium chloride. So now which one of the figures represents which one? So if we take a look on the periodic table where each is located. So we're talking about sodium, which is atomic number 11, and magnesium, which is atomic number 12. And so we know that the further to the right on the periodic table, the smaller the atom. And we also know the more electrons that you rip away from a cation, the smaller it becomes. So we know that magnesium 2 plus is going to be very much smaller than sodium. Now, if we compare O2 minus versus Cl minus, we can see that oxygen is higher on the periodic table than chloride, or oxygen's higher than chlorine. And so we know that oxygen is going to be smaller than chlorine. So whichever sort of picture here is going to have the smaller particles are the ones that are going to be the magnesium oxide. Whichever one has the larger particles is going to be the sodium chloride. So because of that, we can say that that A is sodium chloride and B is magnesium oxide. All right, that's it for the day. Thank you.